Hey there, I'm Joe Carter. If you've ever popped the hood and thought, where do I even start? You're in good company. Around here, we take the mystery out of car repair, one fix at a time. Whether you're a beginner or just looking to sharpen your skills, there's something here for you. Don't forget to like the video and subscribe if you're into learning without the headaches. All right, that's enough from me. Let's get into it.
The figure shows a turbine with variable geometry installed on Volkswagen, Skoda cars. The general structure of the turbocharger and the principle of additional air injection does not differ from conventional turbochargers. The main feature is in the rotary blades, control mechanism and vacuum drive. When the position of the vacuum drive axis is changed, the adjusting ring is rotated by a certain angle. This rotates the vane axis in the support ring. They synchronously change their position, thereby changing the cross-section for the exhaust gas flow. How the boost pressure changes when we considered the principle of operation of the variable geometry intake manifold system, we talked about the dependence of the gas flow rate on the channel cross-section. At the same pressure, the gas flow velocity will be higher in a channel with a narrower cross-section. High boost pressure is necessary for the turbine to quickly reach the zone of efficient operation at low engine speeds. In this mode of operation, the blades reduce the cross-section of the channel through which the exhaust gases travel to the turbine impeller. As a result, the boost pressure increases. Therefore, as the engine speed increases, the vanes change their position, increasing the cross-section for the exhaust gas to pass through. The operating principle of the variable geometry eliminates the need for a wastegate. The entire exhaust gas flow passes through the impeller of the hot part. Excessive boost is prevented by changing the position of the rotary vanes. System in section. The blades are arranged perpendicular to the radial lines to provide a narrow cross-section for the exhaust gas flow. This provides rapid boost and torque gain in the low engine speed zone. Stepped blade arrangement, large cross-section for exhaust gas flow. The same mode is used as an emergency mode when the self-diagnostic system registers incorrect system operation and there is no power to the solenoid valve. Automotive gas turbines of all types have three modes of operation: exit to the operating zone. The spinning turbine shaft creates resistance to the flow of exhaust gases, which reduces cylinder filling and, consequently, engine efficiency. It is with the mode of turbine wheel unwinding that drivers associate the phenomenon of turbo yoke, the zone of effective operation. When the working zone is reached, the compressor wheel rotation speed allows to inject more air into the cylinders, which is felt by an increase in torque, overspin zone. The design of the turbocharger suggests efficiency zones. The engine is also designed for a certain amount of boost. If the exhaust gas flow rate exceeds the optimum efficiency zone and the design boost value, further use of the turbocharger will only reduce engine efficiency. Also, exceeding the design impeller speed leads to airflow stall. That is why most turbines are designed with a valve that bypasses the turbine wheel at certain engine speeds. The design of a fixed geometry turbine is always a compromise between speed to efficiency zone, boost rate and peak power limit. These parameters are influenced by the diameter of the gas flow channels, the ratio of inducer to exducer area, radius housings. Wastegate valve design, blow-off. But due to the fact that the turbine characteristics are laid down at the design stage, its working area is rather narrow. Advantages: active modification of the channel cross-section of the hot part of the turbine allows to expand the effective operating zone. Cars with variable geometry turbocharging can produce more power from low speeds. Reduced exhaust gas pressure at high speeds. Due to the absence of the wastegate valve in the hot part, the number of multidirectional gas flows is reduced, which improves the flow of gases through the turbine. Improved engine elasticity. Reduced fuel consumption and emissions. Possible malfunctions. In conclusion, understanding the principle of operation of a variable nozzle turbine, or VNT turbine, is essential for optimizing turbocharging efficiency. By addressing the limitations of traditional gas turbochargers, VNT technology enhances performance across a broader range of conditions. We've explored the design of these systems, identified common fault symptoms, and discussed the importance of regular cleaning and adjustment to maintain optimal functionality. By keeping these factors in mind, you can ensure that your turbocharging system operates at its best, delivering improved power and efficiency. Thank you for watching, and we hope this information helps you in your journey with VNT turbochargers.